P times 1 minus P.
Good study. Anybody else remember that? Okay. All right. Let me give you an example. Let's say P is 0.5. Okay? The probability is 0.5. Then what is the mean? What is the expected value? It's P, 0.5, right? This means so if P is 0.5, I ask a bunch of people, I expect half of them going to say 1, half of them going to say 0. Then average, we take the expected value, we'll take the average, I'm going to get 0.5. Okay? So what's the standard deviation in this case? Give me a number. Zero 0.5. Okay, so just calculate variance, P times 1 minus P, 0.5 times 0.5, 0.25, and standard deviation is the square root of variance, 0.5. Okay? So, does it make sense that standard deviation is 0.5? Remember, half of people is 1, half of them will say 0. The average is 0.5. Remember, standard deviation is measuring the average distance from the mean. If the average case is 0.5, those who say 1, they're half above the mean. Those who say 0, they're half below the mean. Okay? So the average is 0.5. The standard deviation is also 0.5. Okay? All right. So now, if I do this, I'm going to ask a bunch of people, and I do an average over n people, x1, x2, 3, going. Say ask a number of people, say n, say is 100. I survey 100 people, and then I add them up. I divide by n. So this is the definition of sample average. Okay. Another way to write this is really 1 over n times x1, 1 over n, x2, keep going. Okay? So exactly what is x bar? X bar effectively, forget about this is sample average. Just think about this, each x is a random variable. And now I'm just doing a combination, a linear combination of random variables. Okay? So this x bar is also a random variable. Okay? X bar is a random variable formed by taking a linear combination of other random variables. Okay? So let's go back to what we did last time. We did something like this. Okay? If you log return 1 day, 2 day, all the way to t day, let's say t is 2. Okay? In the sum of 2 random variables, it doesn't have to be returns. It can be anything. Okay? Let's say let's use the ETF. Interpret this many ways. So what is the variance? What is the variance of this case? What is the variance of the sum? Everybody still remember the formula? The variance of the sum of variables?
It's the variance of R plus
The both R's.
variance of R1 plus variance of R2
1 and 2.
and covariance.
there any reason why you put T instead of N on the, like,
T equal to 2. That's the reason. There's 2 here. Okay. Alright. So remember we talked about, you know, this diagonal, off diagonal. Diagonal is sigma 1 squared, sigma 2 squared, sigma 1, 2, sigma 2, 1, something like that. Okay? Sigma 1, 2, sigma 2, 1, they're the same thing. So you can count everything in this matrix, the 2 of these. Okay? But these 2 are the same thing. Okay? Remember the definition of yeah, I can introduce a new concept. Sigma 1, 2, the covariant term. Okay, R1, R2 is equal to the expected value of R1 minus R1 bar, R2 minus R2 bar. Then take the product, take the expected value. Okay. So this is deviation from mean for R1, deviation from mean for R2, then take the product. Okay? Let me ask you this. This measure of covariance, does that depend on how you define the returns, the scales? Let's say for one calculation we use R to be basis point. For another calculation we use R to be percentage point. Would that change this covariance measure? Which one will be bigger? Or are they the same?
Can you repeat the question?
If I use R as basis point, okay, for example, daily return mean is say about 4 basis point, okay, versus I use percentage. Daily return is about 0.04%. Okay, would that make a difference in the calculation of covariance? No. Why not?
The same,
It will. But at the end of the day, you got a number, right? When you put, say, 4 here versus you put a 0.04 here, okay, it will make a difference. Everything will be 100 times bigger. This term will be 100 times bigger if you use basis point. This term will also be 100 times bigger. And the whole thing will be, you know, I guess 10,000 times bigger. So covariance, it's like variance. It's not unit-free. It depends on unit you're measuring things with. Okay? If you're measuring in say meters instead of inches, you're gonna have different covariance. Okay? So to normalize, there's a way you can get rid of that effect. You can intuitively you can think like this. Okay? Instead of measuring covariance of the underlying deviations, I first transform each number into the z-score. Take out the mean, divide by some deviation. Okay? And then I do the cross product of the 2 z-scores. Okay? Remember, if you do the z-score, z-score has mean of 0, z-score has some deviation of 1. Then you no longer have the scale effect. Okay? You measure things in inches or in meters or in how many feet. Okay? You're going to have the same z-score. Okay? Because the mean, because the number will change by the scale. This standard deviation will change by the same scale. And they cancel. Okay? Z-score has no scale. Alright? So if you do this, another way to write this is the expected value of R1, R1 bar, R2, R2 bar, divided by sigma 1 times sigma 2. Okay? Or this is sigma 1, 2, divided by sigma 1, sigma 2. Okay? So in the numerator, the covariance between 2 things. In the denominator, you have the standard deviation of 1 and deviation of 2. Okay? This normalized, this term we calculate covariance using standardized z-score, okay? Or, we say this is the covariance divided by standard deviation 1, standard deviation 2. This number is called correlation. Okay? When we talk about correlation is high, correlation is low, correlation is negative, correlation is positive, this is a strict definition of that correlation. Calculate covariance, then you normalize it, standardize it by the standard deviation. Once you do this transformation, sigma 1, sigma 2, this number is bounded between -1 and +1. Okay? So we can say, all right, if two things are perfectly correlated,